is if I have a function that looks like this. So if I take some function and I add or subtract a value outside of it, okay, that represents a vertical shift. Okay, so this one is going to be a shift up k units. And if I take f of x minus k, this is going to shift down k units. Okay, so let me kind of show you how we've already done this. It just hasn't been explained in this way. Okay, so if we took, and all of these are comparing to the original function. So let's just take a linear function. F of x equals x. So this is just the generic linear function. So if you look at this graph, the graph itself looks like this, right? It's just a slope of 1, a y-intercept of 0. Okay, now, if you take and you add something outside of this function, meaning it happens away from whatever is being performed to this function, what you're looking at is, and I'll call it y1, is x plus 3. Okay, so what we would be doing is we take our regular function, our x function, and we shift it up 3. So 1, 2, 3. Would it make sense that this is our graph for x plus 3? Yeah, if I wrote my own book for algebra, I would teach all shifting in terms of this. So it is generic. It works for anything. What if I took a function that was f of x equals x squared? Okay, so here's my generic function. It's just a parabola, right? And what if I took my transformation and I made it, again, this shift is happening outside of the function. So I'm going to take my x squared, and then I'm going to add something or subtract something. So let me subtract here. Minus 3 is happening outside the function. The square, the part of the function, the square is not involved with the negative 3. The negative 3 is happening outside of that. But would it make sense that if I took this function, or this equation right here, and I shifted it down 3 units, 1, 2, 3, that this is what my new function would look like? Okay, now think about, if you plug this in, you're going to see that it gives you that same thing. So when you're graphing functions, you can always very easily use the concepts of vertical shift to sketch the graphs of those functions. Okay, the same is true with horizontal shifts. So let me talk about the horizontal shifting rules. Okay, so now horizontal shifting occurs inside the function. Okay, and so this is where sort of like the composition of functions comes into play. Okay, if I have my shift, or I'm going to call it h here instead of the k, but if I make my adjustment inside the function, okay, this represents a horizontal shift. Okay, and the horizontal shift, depending how you think of the rules, and I'll tell you what I do, but this one is going to be shifted, and it winds up kind of shifting counterintuitive, meaning, to me, I always say the shift is whatever value of x would give you a 0 in here. So what value of x would give you a 0 in our parentheses here? Negative h, right? So is negative to the left or to the right? Left. So this one's going to shift to the left h units. And if I take f of x minus h, what value of x would give you a 0 in here? Positive h. Positive is to the right. So this is going to be a horizontal shift to the right h units. Okay, now, if we come down and we look at these same kind of things with our function, our shifting happening inside the function. Okay, the whole idea of, again, this linear function is x to the first. If I take, and I'll call it y3, and I take my shift, my plus 3, and I put it inside this function. So x plus 3 all to the first. Does that change anything? X plus 3 to the first is still just what? X plus 3. Okay, and let's see, does this allow you to do the same shifting. So here, based on this, what value of x would give me a 0 here? -3. So instead of thinking of being shifted up 3, we could also think it gets shifted 1, 2, 3 to the left. Is it going to give us the same equation? Yeah. Okay, what if I took, and let's take another function. Well, let's do the squared function. If I took my function x minus 2 and I squared it, if I use my transformation rules, I'm going to take this parabola, this U shape, and I'm going to shift it which direction and how many units. So what value of x would give me a 0 in here? 2. So plus 2 is to the right 2. So if I took this graph and I shifted it 1, 2, and I drew my same parabola right here, that is the correct sketch of the graph. All right, the first one is a reflection where there's a negative outside your function. So again, using composition of functions, you guys understand what I'm saying, outside versus inside the function? So when the negative is applied outside your function, the reflection is going to be across the x-axis. Right, it's reflected vertically. Okay, and so the way that this, again, applies is, and I'll go maybe y5, if I have negative x squared. So I'm going to take my general, here's my x squared function, my generic kind of base function. The negative on the outside means I'm going to flip this across the x-axis before I do any of the shifting. And this reflection occurs before shifting. And so you think of that before you shift it. So if I have negative x squared, I'm just going to take that graph and I reflect it kind of on that vertical, kind of mirror it across the x-axis. Okay, whereas if my negative occurs inside my function, so notice the way I write it, f of minus x, the negative is inside. Now my reflection is going to be across, what do you guess? Yeah, the y-axis. It doesn't really apply to the x squared, the parabola, because it's symmetric across the y-axis anyway. So let's look at this in terms of, let's see, we'll use the square root that we just did. Okay, the square root of negative x. Okay, so now my negative applies it's applying inside my function, not outside of it, right? So when I look at my graph for this, I'll sketch it in blue. Okay, my original graph would look like this, but if the negative happens on the inside of my function, it gets shifted kind of like this, mirrored across the x-axis. So the actual graph itself would now look like this. So notice how these affect the domain and ranges, right, when you have these reflections. So here the domain and range, again, it doesn't affect the domain on this one, but the range gets inverted completely. Here, it doesn't affect the range, but the domain gets inverted completely. Okay, so what I'm going to do here in the next is I'm going to go through some examples where there's all of the different kinds, the shifting and the reflecting. Okay, so let's take a look at how this works. All right. So here is your graph. I want you to see, if you can, without using your calculator, identify what the sketch of this graph would look like. And also find, in this one, you don't need to find domain and range because it doesn't change. Okay, but see if you can sketch this graph for me, please. All right, so what I wrote here in this light yellow color is the generic form of the outer function itself, the cube root function. Okay, so there's a couple things that are happening to it. Is the negative inside or outside the function? It's outside. So where's the reflection occurring? It's reflected across the x-axis, right? In this case, it winds up, it doesn't really matter because they're both the same, right? If you reflect it on the x-axis or the y-axis, you get the same thing. So let me kind of draw this in stages. So my next stage, I apply my reflection. So this is y equals negative cube root of x. Okay, so I still have my common reference points here. So now I can take this red graph and go through my transformations, my shifting. So what is my vertical shift here? Vertical shift is up 4, so 1, 2, 3, 4. So once again, if I am just going kind of piece by piece, I now have this graph. This is y is equal to the cube root of x plus 4. And then my final graph, which I'll do in a solid line in black, so you can draw over all of these. But here's my critical point now is I've reflected, vertical shift. What's my horizontal shift going to be? 1 unit to the, what value of x would give you a 0 inside here? 1, so it's 1 unit to the right. So here's my final shift. And now if I just go through my general form of this equation, I get my overall graph. Okay, so I've taken into consideration the reflection, I've taken into consideration the vertical shift and the horizontal shift to get my final graph. All right, now, you guys do have access to your calculator, so let me show you really quickly how you would do this on your calculator, kind of verify. But like I said, if you understand these, this is probably quicker than doing it on your calculator if you kind of understand the process. Okay, but if you're using your calculators, the first thing that you would want to do is enter this equation in your y editor. So if you go green diamond, F1, get to your y editor. Okay, now there are no cube root buttons, so how would we have to express that on our calculators? X to the power of 1/3, right? So when you look at this, we do have to make a quick little adjustment, x minus 1 to the power of 1/3. Okay, so this is how we would need to enter this. Hey guys, I'm not going to help out on questions on this. If you can refer to your notes, okay, and I'll explain your notes to you. Okay, so when you look at this, you do have to enter it in that alternate form, the rational power form. So x minus 1 to the power of 1/3 instead of the cube root. And then the plus 4 occurs outside. And then once you have that entered, you can now go to your graph. I'm going to check and make sure my window's set right. Okay, and does this graph resemble what we were expecting? Yeah, so we know what point should this be right here. What are the coordinates of that point? Right here has an x coordinate of 1 and a y coordinate of. So if I go through here just to confirm that I have the right thing here, if I hit F5 this math and I want to find the value when x is 1, what am I expecting it to show? 4. And when I get that, I see the 1 of 4 is the correct set of points. All right. So that's all I wanted to kind of talk about. The domain and range when you're dealing with uh, odd indices. So just like in odd powers as well. So cubes and x to the first, x to the fifth. Um, your domain and range are usually less limited, but you can use your calculator to figure out domain and range restrictions. Are there any limits on our domain here? Are there any restrictions on what x can be? No, it can be negative infinity to infinity. What about our range, our y's? As flat as these are they increasing as you move? Yeah, so they're going to continue to increase, so there's no limit on the range either. So for this particular problem, if you had to find the domain and range, you're looking at negative infinity to positive infinity for both. And if you guys remember the way that these need to be entered online, negative INF to INF for both of those. I know it's been a while since we did interval notation, but you are going to see those in there.